Dasher and Dancer and Prancer and Vixen, Comet and Cupid and Donner and Blitzen. But do you recall? Sorry, I got a little bit distracted there. So here we go, 10.5. Find the probabilities of independent and dependent events. So independent events are two or more events that have no influence on one another. For example, if you're going to roll a dice and flip a coin, whatever happens here isn't going to be affected by what happens with the coin. Dependent events, multiple events where one event affects the outcome of a later event, and I'll show you that in a minute. Conditional probability. The probability an event can occur within a smaller context, written P, probability of B given A. The probability that B occurs given that event A has already occurred. So we're going to look at all those kinds of things. So first of all, do the warm-up and come back. He knows, and if you ever saw it, you would even say it glows. All of the... So this is what you should have gotten. Two six-sided die are rolled. This is just kind of like the homework that you did in 10.4. Find the probability of each sum. The denominator, the total combinations are 36 when you have two die. And these are the different ways you could get a total of 7. And there's 6 ways out of 36, so that's 1 over 6. This would be 10 out of 36. There's 10 ways to get a sum of 5 or a sum of 7. And then this is 1 over 8. If you flip a coin, there's the first toss, the second toss, third toss. It's all one chance out of 2 in each toss, which when you multiply together you get 1/8. So first let's talk about the probability of independent events. When one event does not affect the outcome of the other event. And you just multiply the two events together to find the probability of those. In a survey at a football game, 50 of 75 male fans and 40 of 50 female fans said that they favored the new team mascot. If one male and one female fan are randomly selected, what's the probability that they both favor the new mascot? Well, they told us for the male, it's 50 out of 75 that favor the mascot. For the females, it's 40 out of 50. So we just multiply the probability of both of those events together to get the total probability. And that would be 8 out of 15, which is approximately a 53% chance that if you randomly pick a male or a female, they're going to like the new mascot. So that's how you do that. A survey found that 46% of parents surveyed say that they read to their children at least once a week. If 3 parents are selected at random, what's the probability that all 3 will say that they read to their children at least once a week? So we have 3 events, okay, 3 parents being drawn. The first parent, the chance of them reading to their parents or to their kids is 46 out of 100. The second parent, it's the same thing. It's not affected by what this person said. The third parent is also a 46 out of 100 chance, because that's how you write percentage. So you just multiply those all together, and you get 97,336 divided by 1 million, which is approximately 0.097, which is only a 9.7% chance that if you choose 3 parents, they're all going to say that they read once a week to their kid. So that's independent. Oh, I'm sorry. Look at, we have one more situation that's independent here. So the reason it's independent, well, let's read it first. It's a story problem. During each of the 5 days of a special week, an employee is randomly given one of 10 prizes. All prizes are available each day, and one of the prizes is a $500 gift certificate. What's the probability that an employee receives the $500 prize at least once? The reason it's independent is because each day is a new chance. It's not affected by what happened the day before. Now, I think that the easiest way to do this is to solve it using the complement. If you do 1 minus the chance that they won't ever win the prize each day, that'll give you the chance that they will win the prize at least once. So this is going to have to be written sort of like a combination. first of all, in the bottom, it's going to be 10 chances, choose one, every day. That's the total ways you could possibly win, or not win. In the numerator, you're going to put the ways you can't win. And there's 9 ways, choose one. Because there's 9 of them that aren't going to give you the prize. So this is the probability of not winning. I'll just write that out. The chance the employee, this whole thing here is the chance the employee won't win the prize each day. Okay, what this is going to equal is 1 minus, this becomes 9 choose 1 divided by 10 choose 1 is actually 9 over 10. Oh, I forgot a very important number. We have to take this, and this is going to happen every single day, and we have 5 days, so this has to be raised to the 5th, 1 for each day. It's the same thing. You have a 9 out of 10 chance of not winning every day, and we have 5 days. So we have to raise it to the 5th power. And then we do 1 minus 0.9 to the 5th, which is approximately 0.41. So this is giving me the chance that I have to win at least once, which is about 41% chance. That's a pretty good chance, if you ask me. All right. Probability of dependent events. This is when one event depends on what happened before it. The table shows the status of 200 registered college students. What is the probability that a randomly selected student is female, or if female, is a full-time student? So let's just go back up here and kind of read what the difference is. If you have a dependent event, you take the probability of the first event and you multiply it by the probability of the second event, given that the first event already happened. That's what that straight up and down line means here. So let's look at what we have here. We want to find the probability that a randomly selected student is female. Well, it's only one event, so we don't really need to worry about whether it's independent or dependent. There's only one event. So first of all, though, we have to consider the total amount of students. And if you add this all up, you're going to get 200 in the total amount of students. And there's 80 part-time and 40 full-time, which equals 120 female students. So a randomly selected student is 120 out of 200, which equals 3/5. There's a 3/5 chance you'll choose a female. All right, now the second part here says, what if female and a full-time student? So again, we have to think about, okay, well, I'm going to choose from the females, which is only 120, and I want to decide whether, find out the chance of getting a full-time student out of the female students. It's 40 over 120, which is 1/3. Now, neither one of these are really dependent. We're getting to that. You've got a 1/3 chance there. Here we start to look at independent and dependent. You randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is a heart and the second is a club if, well, before we do this, I want to remind you that all the cards are on page 690 in case you're not real confident with a deck of cards. All right. What's the probability that a first card is a heart and the second is a club if you replace the first card before selecting the second? So we kind of have 2 events happening here. The fact that you replace the first card tells me that it's independent, because pulling my second card isn't going to be affected by what happened by the first card. I'm still going to have 52 cards to choose from the second pull. So if I want to find out the chance of pulling a heart, it's 13 out of 52. I'm going to multiply that by the chance of pulling a club. It's also 13 out of 52 because I replaced that first card. And that equals 169 over 2704. And if I go to my math button on my calculator, I can reduce that fraction. And it's 1 over 16, which is equal to, I'm going to write it as a decimal, 0.0625, and as a percent. It's about a 6.3% chance of that happening. You should try it out. Get a deck of cards. See how often you pull a heart and then pull a club. It's not going to be very often. All right. Now this says you do not replace the first card. That means that my second event is affected by my first. So this is a dependent. Okay. So I'm going to say, what's the probability of pulling a heart? The first pull is still going to be 13 out of 52. And now I want to know the probability of pulling a club given a heart. So I already took one out. I still have 13 clubs to choose from, but I only have 51 cards in the deck now because I didn't put that first card back. So that equals 169 over 2652, which reduces to 13 over 204, which is approximately 0.0637, which is approximately 6.4%. And that's actually a little higher percentage, which is interesting. You have less cards to choose from in the second pull, so it increases your chances of getting a club. There you go. All right. Suppose your area has 8 different internet service providers, ISPs, and you and 3 friends, oh, that's 4 total, randomly select your own ISP. What is the probability that you all choose different ISPs? Okay, so there's 4 of you. Let's say you get to choose first. Out of 8, you have 8 to choose from out of 8. Okay, and then you're going to multiply that by your first friend, then chooses. But since you already took one, they only have 7 out of 8 to choose from. Okay. Then the second friend only has 6 out of 8 to choose from. And the third friend and the last person only has 5 out of 8 to choose from. So that would be 1680 divided by 4096. It's going to be approximately a 41% chance that you all choose different ISPs. And that is that.
Join in any reindeer games. Then one foggy Christmas Eve, Santa came to say, Rudolph, with your nose so bright, won't you guide my sleigh tonight? Then how the reindeer